In this video, we'll go through example 1.2.3 from the book. So in this example, we imagine that we have a population of students at a certain college whose average mean GPA is 2.74. That is the mean for all students at the college. So notice and draw your attention to those words, because then you can recognize the difference between your statistics and your parameters. This is for all students. That's the entire population of students, which means this is a parameter. This is the parameter that is a mean, and so it is mu. Mu is 2.74. Okay, and now they say, suppose we collect a sample of 85 students. Sample size is 85. And we record our sample's average GPA. So we would have a list of 85 numbers, the GPA of each of those 85 students. We'd add them all up and divide by 85 and get their average. And that average would be a sample statistic because it comes from a sample. And since it would be a sample mean, it would be an X bar. All right, they didn't give us that actual sample statistic in this problem because that's not relevant to what we're going to be asked to do, but that's what that would be labeled. All right, so then they give us a simulated distribution of sample statistics. We see the little squares there, and we see that normal distribution shape that we see with our distributions of sample statistics. This one was generated with a computer, which we'll learn to do in a future section. This distribution shows what we expect the simulated sample means would look like if the population mean is 2.74. All right, so now let's answer some questions related to this. The first question asks us to identify the contextual meaning of each square in the distribution. Remember, each square represents a sample statistic if we know that the true population mean is 2.74. So each of those little squares is an X bar, a sample statistic from a simulation where they collected a sample of 85 students and found their sample mean of the 85 students. The next question asks us to describe the shape of the distribution and asks if our sample statistics appear to be roughly normally distributed. And as I said a moment ago, it does appear to have that normal shape to it. It is bell-shaped, right, with the peak in the middle around 2.74, that population mean. Third, it says to estimate the mean of the distribution and explain the contextual meaning. So remember, your distribution of sample statistics has a mean right in the middle, and it looks to me like it's around 2.73, 2.74. I would say it's around 2.74 because the population mean is 2.74, and your distribution of sample statistics is always going to be centered around the population parameter. In this case, the population mean, the mean of all students on campus, is 2.74. So when you go out and you collect samples of students from that campus, you'd have about half of the groups would have a mean higher than 2.74, and about half of the groups would have a mean lower than 2.74, and most of them would be around 2.74. Very few of them would have a mean much higher than 2.74, and very few of them would have a sample mean much lower than 2.74. So it is normally distributed with a population mean of 2.74 as the distribution in the center. Lastly, we're asked to estimate the standard deviation of the distribution, and we're asked, what is the other name for that standard deviation of the distribution? So recall that the other name is the standard error. The standard deviation of the distribution of sample statistics is often called the standard error. So the first thing I do is I kind of overlay my normal curve, and I remember that the middle was 2.74. Looks to me like this one is about at 2.76. This one maybe is at 2.78, a little before that other label. This one seems like could be 2.78 2, I guess, and this is 2.70. They're all 0.02 units apart, and the distance apart is that standard error. So the distance apart is the standard error. The standard error is approximately 0.02.